per lo sviluppo della motorizzazione agricola e industriale, motori diesel lombardini, motori a scappio intermoto.
This is the legendary Dino Ferrari circuit at Imola, Italy. It's April 1986. Imola is the shrine for these fans who are known as the Tifosi. Roughly translated, Tifosi means touched by the wind. But the Tifosi are stirred by power. They are not followers of drivers. Instead, they worship this car, the Ferrari 186. The Tifosi know every detail of its brutally powerful engine, of its scarlet carbon fiber fuselage, and most of all, they love its spectacular, twitchy chassis. Formula One is the stuff of Italian enthusiasm. The Tifosi are literally high on technology, especially when Ferrari wins. Behind the razzmatazz of Formula One is a rarely seen world of skill and inventiveness. Gone are the oily rags and the flat-capped amateurs. Here, computers, rubber, metallurgy, synthetics, electronics, and aerodynamics consume fortunes. This team alone confesses to spending £7.5 million a year, but probably consumes about twice that. Formula One is a technological dynasty, a dueling ground for the big multinationals. But for today's Formula One engineers, the big question is how to tame the fiery, unpredictable turbo. Brands Hatch 2 years earlier. This is the 1984 British Grand Prix. It was during this season that the high-technology world of Formula One engineering first started to establish a method for taming the turbo. Apart from this normally aspirated 3-litre Ford Cosworth powered Tyrrell, all the cars are 1.5-litre and turbocharged. Hidden beneath the international sponsors lurk the even bigger automotive manufacturers. This Parmalat Brabham is not powered by Italian cheese, but German BMW. And its turbo engine is now mated to this, a Bosch onboard computer. It is literally the engine's brain. In 1984, these electronic black boxes are still relatively primitive. Because for the computer programmers, Formula One engine management is a completely new problem. This is engine designer Keith Duckworth. Duckworth is the fallen prince of Formula One. His motor racing masterpiece was the now outdated, unturbocharged Ford DFV. Duckworth is at the British Grand Prix as a mere observer, to watch BMW, Honda, Porsche and Renault rise to take his crown as the most successful Formula One engine designer ever. Of particular interest is the fast-developing Japanese Honda engine in this Williams car. Even Lotus have newfound power with their French Renault turbo engine, controlled by its Bendix computer.
They're working apparently on a 6 and on a 4.
But the man with Duckworth is Mike Kranofus, an affable German-American and head of Ford Motorsport.
Yes, I've seen it before, yeah. Oh.
He shares wisecracks with Duckworth about the influence his designs have had on this new generation of engines.
I think you could say that after a couple of more years of seriously thinking, they have come to the same conclusion you came, or you had arrived at 67.
Although the enthusiastic crowd sunburning in the warm English summer couldn't have known it at the time, It's at this race that Ford and Duckworth finally agree to build a new engine.
We ought to start again.
Or to start again what?
Make a new engine.
But there are many who say that Duckworth's distaste for turbocharging will prevent him ever designing another successful engine. It's a view until recently shared by many within Ford itself. Vice Chairman, Ford of Europe, Walter Hayes.
I didn't really like turbos. I always felt our engine was an old master and turbos were modern art, you know? And I don't want to sound like a fuddy-duddy, but I think it's a very fair description of where I felt the difference was. When our traditional teams started to be beaten by the Renaults, and what I still think was a distortion of the regulations, I'm not complaining. I don't believe that 1.5 litres turbocharged is equivalent to 3 litres unturbocharged.
But the rules said that turbocharging was legal, and it was another major manufacturer, Renault, who realized its potential. At the 1977 British Grand Prix, this small black and yellow car qualified for the first time. The engine was based on a normal road car and simply turbocharged for racing. No one took it seriously, except, of course, the unconventional French engineers at Renault. Probably because motorsport's governing body is also French, the turbo was allowed to survive. This is a road car turbocharger, but the principle is the same when applied to a race engine. The power of any engine is limited by the amount of air it can breathe in. A turbocharger uses energy from the hot exhaust gas, which is otherwise wasted, to power a compressor. This simply pumps compressed air into the engine, producing more power. The turbo itself consists of a gas turbine connected directly to a compressor by this shaft. The exhaust gas spins the turbine and forces the compressor to pump more air. The more air, the more exhaust gas, and the more exhaust, the more air. Theoretically, a runaway spiral of explosive power. Keith Duckworth.
I think that in any racing engine, the nearer you are to it disintegrating, in general, the better its performance will be.
To combat this excessive turbo power from such small engines, ever-decreasing fuel limitations have been imposed on the teams. So it's for fuel economy that engine management electronics have become crucial.
As soon as you get onto economy, you can't afford to throw fuel in for cooling. Therefore, you have to try and put in exactly the right amount of fuel. Then, if you have any failure or on your engine management system to provide that right amount of fuel, and it goes marginally weak from the weak position that you're already trying to run for economy, you can melt your turbine in a second, or melt a valve or a piston, and you're out of the race. As can be seen fairly regularly.
Turbocharged racing engines can be developed in two ways. Start from scratch, or like Renault, take a ready-made engine block and alter it until it delivers the necessary output. Anything from 700 to 1,000 brake horsepower. Whether developed from an off-the-shelf design or built from scratch, there are two basic engine configurations: the V6 engine and the inline or straight four. The numbers refer to the number of cylinders or pistons, and the word straight or V refers to the arrangement of the cylinders or the pistons in relation to the crankshaft. This is an end view of a straight four. The Italian Ferrari, the French Renault, the German Porsche, the Italian Moto Moderne, and the Japanese Honda are all V6s with overlapping throws onto the crankshaft. This is the end view of the Honda V6. The German BMW and the British Hart engines are straight-4 units. BMW have been particularly successful with this neat, if rather asymmetric, engine layout. But the engine is only part of the story. Tucked into the car are the radiators for cooling the engine, intercoolers for the turbochargers, pipes, oil coolers, exhaust, and the red-hot turbochargers themselves. So it's the reduction in the size and complexity of all this, as well as the reduction in the size of the engine block, that is the main engineering challenge. Compactness and the fact that 4-cylinder engines tend to be more economical than 6s finally led Duckworth to develop this aging 4-cylinder sports car engine. It's autumn 1984. Mike Cranifus and Walter Hayes have set November 1985 as the deadline for the delivery of a race-ready engine. By February, the 4-cylinder prototype is on the dynamometer. The engine is conventional. 2 pulleys at the top drive double overhead camshafts. The rest is just cobbled together for testing. The throttle linkage is operated from within the soundproof control room. Perhaps the only odd feature is the enormous silver plenum chamber alongside the engine. This plenum is where the boosted air is balanced before entering the engine. By making it big, Duckworth hopes to tune the air to match the outgoing exhaust pulses. For early testing, the exhaust is vented without passing it through a turbine. Boost air pressure is delivered to the engine from this yellow industrial compressor, connected to the test cell via a network of heavy-duty pipes. This method of boosting the engine removes the complexity of developing a turbocharger while allowing the designers to vary the air pressure. But as Duckworth admits, sooner or later this clumsy plumbing must be miniaturized and installed in a racing car. Today, the compressed air is 2 bar, about 28 pounds per square inch, the pressure of an ordinary car tire. Using strategically placed sensors, the tedious business of engine mapping begins. The hand on the throttle belongs to Chief Test Engineer Alan Morris.
25.45, 3.8, 86, 7, 17, 4.92.
Boost.
Right, 10,000.
That's revolutions per minute. Mapping, as the word suggests, is the business of recording coordinates, all the data, input and output, at all engine speeds and loads.
4.5.
Right. 25.15.
That's engine load.
4.3.
That's blow-by, air escaping past the piston.
9.
Exhaust pressure.
21.
Intake temperature.
4.92.
4.92 are the milliseconds the fuel droplets take to spread into the cylinder before igniting.
Right, 10,500 coming up.
In its original unboosted form, this modest 4-cylinder engine was limited to speeds of 10,500 revolutions a minute. Beyond this, is unknown territory.
Right, okay, 4.5.
23.05, 4.5, 95, 9, 23.
4.74.
I'll tell you up to 11,000. 11,000.
4.5.
22.65, 4.4, 90, 95. Ah,
We've had a accident.
what happened
Did the
there?
blow-by go?
Nah, it's not
No?
moved. They line up about.
A fibre optic endoscope probes the cylinders as Alan Morris measures the pulleys on the silent engine.
Yeah, you get the centre there, look. That. Difference between there and there, look.
Well, just turn the engine round.
Oh, we can't, that's the problem. It's a little bit tight.
Oh.
The cam drive belt has jumped one notch out of alignment. It's the first outward sign of a catastrophic failure, now confirmed by the probing of Paul Ray.
I think the piston's hard up against the valve, so...
Yeah. But it looks like the inlet and the exhaust are crossing, doesn't it?
Yeah.
If you have a... No, it's not interesting. Go on, have a look.
Yeah, we take it off.
Right.
Two hours later, the engine is in the workshop. Off comes the cam cover. For Paul Skelton, this is the start of the routine, absolutely methodical process of damage analysis. A mechanical post-mortem. To avoid distortion, even on a damaged engine, the bolts must be released in a set order. As the cylinder head and plenum chamber come off, the damaged piston is revealed. The earlier analysis by endoscope was correct. The valves have hit the piston. But so far, there are no clues why.
We've got that much squeeze. Try the rod's broken. Mind his feet.
The exhaust and inlet valves have definitely hit the piston or crossed over. But this can be caused by many things at high engine speeds. General Manager of Engineering Dick Scammell is uncharacteristically nervous about such a dramatic failure so soon.
I mean, because the piston's been hitting the head, hasn't it? I mean, it's been thumping on the head quite a long time, because it's formed the piston into the combustion chamber.
Scammell knows BMW have achieved remarkable reliability and power with their four-cylinder engine. The next clue is in the oil. Tiny metal fragments clatter into the drip tray. The post-mortem continues on the gutted engine. Sinister dents in the temporary steel sump seem to suggest some kind of internal explosion. an overwhelming atmosphere of depression creeps in. To Chief Development Engineer Martin Walters, it looks bad.
Lost it again.
Even now, the crankshaft refuses to turn, as quite large chunks of big end bearing begin to turn up. What they don't know at this stage is that the entire engine block has changed shape, seizing the internal components.
I am puzzled why we can't turn the engine. This is part of the rod. Just having a look to see if I can find the 2 bolts. There's one.
The scattered and broken pieces begin to come together to form a picture of a much larger disease. This little cup of scrap metal is all that remains of the big end bearing, symptoms of an endemic weakness in the engine design.
The problem is there isn't as much heat as I think you normally see when you just lose a bearing. It's only come up about this far now. It normally tends to get a bit hotter. It may be that a bolt broke first.
Excessive heat due to lubrication failure makes steel turn blue.
Just hammered its way out through the end.
With no obvious discoloration, the search for the cause moves away from lubrication failure to metal fatigue.
Practically stretching, doesn't it? Don't you think?
That's been stretched.
Stretch.
So what started the failure?
The bearing going, but why the bearing?
Well, then,
why the
there's
bearing?
not enough heat in that bearing, is there?
Oh yeah, quite a few.
The first lesson that the Cosworth engineers are learning is that even a familiar engine, when it's turbocharged, can fail in mysterious and catastrophic ways.
Done quite a lot of it, actually, because that's out of the pump, isn't it? That's how that's bearing, isn't it?
But can't get in the pump though, can it? Because it's got to go through the...
News of the explosion has reached Jeff Goddard, chief racing engine designer.
What do you think went first? Just bolt failure, wasn't it?
Well, I don't know, because there's something odd, because we can't sound the cracks.
Goddard, an expert on metal fatigue, has never been happy with the plan to turbocharge this old 4-cylinder engine block. As the pistons are forced out one by one, it becomes clear that a massive explosion has occurred. What's worse is that it all happened well below race boost pressures. The omens are not good. 5 more 4-cylinder engines fail in the next 3 weeks. Eventually, the cause is traced to incurable vibration at the crankshaft. They are little over a year away from the first scheduled in-car test, and back where they started, without an engine.
Yes, it's still the
Round
same.
through there and up here, isn't it?
It's just got less on the shaft rotating with you. Piston ring seals, we are on piston rings. The torque today,
Yeah.
they haven't got anything.
They haven't, that seal doesn't work.
400 psi, forget it. 15 is a max.
Towards the end of 1984, the atmosphere of gloom over the failure of the four-cylinder engine is replaced by optimism. Funding for the design of a completely new engine has been agreed. It will be a Ferrari-like V6.
The end needs
Keith Duckworth.
The choice of a V6 is on the basis that most people are using V6s who are successful, and that therefore, whichever way the rules go, we feel that they will be to suit V6s. The 120-degree V6 does allow you to fit two standard turbochargers in the conventional position, one on each side of the engine, and therefore you can in fact join the rest of them in the now established situation. And then
Duckworth has always believed that turbo energy is wasted merely pumping air. Eventually, he intends to take a drive off one large centrally mounted turbo and feed it back into the engine. It's the revival of a pre-war idea known as compounding.
then proceed with the compounded setup. The additional point is that as we have not got a team sorted out with whose engineers we can discuss the layout of the car, and the amount of intercooling that you need for the compounded layout and the weight and the whole complexity of it means that an awful lot of discussion with a team would have to take place. Whereas if we, in practice, make a standardish looking V6 with the twin turbo layouts, then we know enough about car design and the intercooling requirements, and it's sufficiently near the normal swing of things that we should have a very good chance, even if a team isn't selected till late on.
The choice of which team will have the new engine is a problem for Ford to solve. For now, Duckworth's designs are in the hands of men whose craft would have been recognized by the great engineers Brunel, Telford and Stevenson. This is the Zeus Pattern and Tool Company in Birmingham. Here, flat blueprints are turned by skillful carving into three-dimensional wooden formers from which molds can be made. Seasoned Brazilian mahogany is chiseled, honed and polished until the grain is as smooth as steel. This is the crankcase end, and this will be the pattern for the main engine block. Several hundred Formula One engines do not warrant an investment in computer-aided design. All that's needed is a calculator, a notebook, and 2 centuries of engineering know-how.
That's what he should have gone behind the flange.
It's a draftsman's error, isn't it?
Well, that's who we're blind, man. Tell you, we were already from the 15. You tell me how many you're going to pinch it. If I pinch another 5, we should have 20 because that's the 15.
Even at this stage, flexibility is crucial. Long and painstaking discussions tease out the best way to solve minor design difficulties.
Taking a corner out of this one and then going down.
That's right. I've got to get to the other side of the flange.
That's right. That one, so that side's accommodated for you, isn't it? Brian's already put that right in your Brian.
Yes. Yeah, it's a good job I noticed that. the shape of the 2 degrees out from the
That's
print.
right, we've got it on this side. We've got loose pieces on this side.
Just
like,
one loose piece on the... Oh, but that... I don't get none of that anymore. That's only past the flange.
That's right.
Within hours of the pattern being finished, the first cylinder head has been cast in its silicate sand mould at a foundry in Worcester. The valuable sand is broken away and recycled to be packed again and again around the mahogany former. For Formula One, this rough lump of cast aluminium marks a rare event, the birth of a completely new engine. This casting will never be used. Instead, it will be sliced and analyzed to check its strength. Chicago-based Beatrice is a huge American trading company. In February 1985, at the highest level, Ford and Beatrice do a deal. The result is an aerospace quality engineering company on a windy industrial estate near Heathrow.
The engine's going to tie up with that very nicely.
Yes, the electronics will be the last sort of thing in the file.
Yeah.
Which
When will we
determines
get an
everything
actual
else.
engine as a lump, the metal part?
We
rather
should
than
be able
It will build a racing car exclusively for the new engine.
that in about 3 weeks.
The other car...
The first driver is to be ex-world champion Alan Jones.
Yeah.
There's too much of an angle that way.
Yeah.
And it's too much of a load on your wrist. If you're turning, if it's on an angle that way, well, then the wrist has to go like that, and it's putting a strain on it. Whereas if the wheel is more up and down, and then it's just a straight movement with your elbows.
Otherwise, if you're really up there, you're riding like a London bus.
Absolutely,
Yes.
and you're putting
right
unnecessary
over
work on your wrists. Whereas if it's more upright, you do it with your arms. So that's...
John Baldwin is the chief designer.
You haven't got any problems with that on the
No,
news?
that's okay now.
Because that is higher than the other car.
Yeah, no, that's fine.
So...
And if I was to go back further, it would make that even better.
Yeah, because we've now got the shape of your back anyway, so what we can do is actually design your seat, the start of your seat, instead of doing it the old way. So I can block up, so we can put this shape into the car and then start to foam and make the seat to fit you. And you've broken
Detachable steering wheel.
It's only there for
Another one I've broken.
Within weeks, the first aluminium castings are ready for machining. This 120-degree V6 block is turned upside down so that the crankshaft can be eased in.
If you're not careful with it, it's going to hit the side of the block and could cause, you know, quite a bit of damage to it. So you have to be very careful whilst you're dropping it in.
Because of Duckworth's obsession with structural strength, the engine is not easy to put together, and there are many tricks to learn.
And they've got locating pins at the bottom as well. You've got to try to feel your way until they fit.
After every race, each engine will have to be rebuilt. A year from now, Alan Eldridge will probably be able to do this blindfold.
I think that's about it.
Now, special blocks are temporarily fitted to the crankcase studs. The studs take short bars, which can be expanded with a spanner. This spreads the engine block by a few millimeters to allow the bearing cap to slip down and bear on the crankshaft. These bearings do two jobs. They hold the crankshaft, spinning up to 12,000 revolutions a minute, and they act as strong bridges or buttresses joining both sides of the engine block. Before the expandable bars are removed, the bearing caps are bolted down. The process of spreading the block is repeated for all four bearing caps. Now the pistons. 3 in each bank of cylinders. A special cup helps Eldridge slip them into the bores. These pistons are made in Germany, but once the engine is proved, Cosworth will manufacture their own. The pistons are very special. Hollow galleries in the top or the crown circulate high-pressure oil. The oil will be injected as the piston descends in the bore. In effect, the pistons are oil-cooled. But this first drop of oil is just to help put the engine together. The crankshaft is turned. This is one of 6 big end bearings. These are the bolts that failed on the old 4-cylinder engine when the bearing seized. They will have to cope with hundreds of tons during a Grand Prix. These seals sit on the cylinder bores. In this engine, the bores, like gun barrels, are separate tubes known as liners. For simplicity, oil for the separate cylinder head is forced through external steel tubes. cylinder head bolts are angled, a typical Cosworth answer to a tricky problem.
The original reason why we angled our head bolts was to allow you to have them coming through the head and yet missing the cam shafts, because the most convenient position is in the same line, and that is what caused a lot of engines to have to be separated with the head bolts below and a separate cam carrier. Allied to that one, we then were looking at liner situations and the best way of making a head joint and liner. And I devised a scheme of a liner which the head was nominally clamped on top of the liners and the liner split was fairly low down. But then the stiffness of the top of the liner and its support was not adequate. And therefore, the angle bolt puts in a component squeezing the two sides of the block together, and therefore will tie and increase the stiffness at the top of the bore where the gas pressure is the highest.
Weighing about 100 kilograms, the first engine is complete. But another, potentially more powerful engine is still proving difficult to finish. American Frank Rayo from Motorola and British electronics engineer Steve Taylor are still hunting the bugs from the prototype engine management computer.
This is called eliminate all the noise you possibly can so the engine runs.
Engine runs, full stop.
Yeah, when it gets back...
Hang on, Frank, you got a short back.
See, it shorts out, huh?
Yep.
That's the one.
It's on one on that line there. One of those is not the right one. Gone, right.
Yeah, we've done so much to the circuitry and software.
Yeah, but I just want to prove it, all right? I want to put it back to its original mounting.
Okay, check the grounds now.
It's 4 in the morning. They've been working for 18 hours, only to discover what many other Formula One engineers already know, that electromagnetic pulses from the engine play havoc with the delicate memory circuits in the microprocessor.
These are all tied to ground now. Pin 5.
Yeah.
10.
Check.
See, there's a piece of solder in here.
This painstaking detective work is the only way to hunt down rogue signals.
5, 6, 7, 8, 9, 10, 11, 12, 17, 20, 24, 25, 7, 28.
You've done 27.
25.
Yeah, well, 27 here should be VSS minus.
27, 28.
You've done that.
Okay. How about this one?
Yeah, but that's the one you said we were shorting out on.
Here, let's verify it. It could be 29.
Ah, it should be open.
Hold your meter on that. I could find out which one it is.
No.
Change?
No. 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 No.
See right away. It's amazing how.
Yeah.
There it is right there. 25, 26, 27, 28, 29, 30. Oh, 30 is a ground.
Well, why is it pulling supply down?
It was open. We tied a V-band to it on one case.
Good.
Okay, so that's all set. We have a big ground path. All those paths you just said were grounded, right?
Yes. No, it's ignition diagnostics.
IDM. We're not using it.
Right.
Okay, so when you're at engine per, we appreciate all these kludges.
Make sure you haven't grounded anything on the way. We're looking good, Frank.
Good. The final test is running this piece of wire to case crown.
Is that the last one?
Yeah.
Fantastic. Looks like you're buying the beers tonight then.
Yeah, no problem.
Known as a tub because the driver sits in it as if in a bath, this main part of the racing car is a composite made from carbon fibre. Formula One engineers are world leaders in the use of this strong, ultralight aerospace technology. The two halves of the tub are bonded together. This steel jig will hold the two halves in place until the bond has set. Perhaps the first driver owing his life to carbon fibre was Britain's John Watson. After this 150-mile-an-hour crash at the 1981 Italian Grand Prix, he climbed from his McLaren's composite tub without a scratch. Peter Turland built that tub for Watson.
The bond takes about 3/4 an hour to go off.
This tub is for Jones. But the engine is still so secret, even he isn't sure of the specification.
There's an engine plate on the top, which lays along at the angle of the engine, which is probably 45 degrees, or I think it's 45 degrees on this one. I'm not quite sure, actually. And then it's hooked to those 2 points there, like that one and that one.
The V6 turbo is on the dynamometer in Northampton. Frank Rayo arrives with his engine management black box.
You want boost also?
Yes. Yes, stick boost.
Yeah. Okay, absolutely.
Well, there's reference.
Oh, maybe I'm on the wrong.
Steve Taylor and Ford software expert Jim Coates from the States set up the monitors.
Okay, it's that one. That's our spout line. That's on the current probe as well. Right. Good.
Steve?
Yeah.
This timing light still flashing?
Initially, yes, please, just to verify.
How do you want to set these up? Want to put an injection up at the top here?
Yeah, start with injection from the top.
Pair of headphones.
Yeah.
Okay, so
On the dyno, this is the most likely place for that to happen, too.
From Ford Electronic Engine Development in the States, Bob Stelmazak has watched over the program for a year. Now the final minutes tick by.
Yeah.
Right, that's it, we're ready.
Can you look after that for
Oh,
me?
certainly, I'd be more than happy to.
Because the engine map is incomplete, these two manual controls will override the computer. The left-hand dial controls spark advance, the right controls the fuel injector pulse width. Exactly 20 years ago, Duckworth's legendary DFV engine was fired up on this same dynamometer. The new turbo seems reluctant to follow.
Go.
Reset. Just see if she'll
Yeah, let's see if we can
come
clean
on
it out before we hit it.
For a moment, there's confusion. Stelmazak asks whether he should expand or reduce the fuel pulse.
They have a check.
Here you go, here you go.
Now what you got?
we should find out what the pulse width is in this state it's running in to find out if we're... Yeah, I mean, I got to find out what pulse width we're at to know what the mix ought to be. Yeah. I can't see it from here. Can you guys get any idea?
What division you're on? Let's say about 1 division, whatever that is. 1 millisecond.
Are we tricking anything out there, like engine cooling or anything that's not picking up an appropriate signal?
No, we shouldn't.
For Stelmazak, this first encounter with the frustration of Formula One technology is infuriating. Back in the States, his boss, Mike Cranifus, will want good news. Right now, there isn't any.
No, we have to find out what we're doing. This isn't going well.
Attenzione prego, la motoristica della variante bassa deve essere rimossa con la massima urgenza. Ripeto, la motoscopa che si trova alla variante bassa deve essere rimossa con la massima urgenza. Signor Chiappini, con urgenza al